Hello again. So this is a new unit for us. We are ready for the star unit. Happens to be my favorite unit. And so we're beginning with chapter 5. You do have a new study guide. It's going to include chapters 5. And we do jump around a little bit. So we'll go to like chapter 9, 10, and then 11. So do pay attention to that. But this is our new unit. And we do want to start off the What Are We summary. And it says we are sunlight. We actually depend on our survival to the sunlight. I mean, we use it in the fuel, so the coal and all that energy that we get has come from the sun. So we do owe our survival to the sunlight. We are sunlight. So chapter 5 is going to get us kicked off. We're going to take a perspective of and use our closest star, the sun, as a reference. And then we'll branch out to the family of stars. And there's quite a few interesting characters in the family of stars. But we want to begin here with our closest star, the sun. So let's get going on that. So definitely we last time introduced to you the tool of a spectrograph, right? The little scope you kind of look through and then it produces a spectrum. So what we do, scientists are realizing that those spectral lines were related to the various types of atoms that were in celestial bodies. And so when they looked at the sun's atmosphere, a window finally opened that we realized we could figure out the composition of the sun. The true nature of the sun was one thing we could figure out. So it really did determine the chemical composition of the sun, what types of atoms were in it. And we could measure the motion of the gases on the sun surface and in its atmosphere. So we'll look at sort of the Doppler effect that helps us with that, and detected magnetic fields that drive the sun's activity. So there's this idea of sunspots that have been reported and visualized. Even Galileo, with his telescope, observed sunspots. And so we'll take a look at that activity of what's exactly generating the sunspot cycle. Okay, so spectral lines in the spectroscope, I mean, it really revolutionized astronomy. So the sun is very simple. It is a great ball of gases that's held together by its own gravity, tremendously hot in the interior, high pressure, and so there is sort of this hydrostatic equilibrium that is going on with our sun that's creating it so it's just not, either imploding or exploding. So there is a nice balance, a simple structure that's balanced between these opposing forces of the collapse from gravity, but yet the expansion because of its generation of its own energy. So it's a nice balance in there. So we can study it and use it as our reference and give us insight to the rest of the stars, the star family that we talk about in the universe. So another reason to study it is that life on Earth critically depends on the sun. So even just very small changes in the luminosity of the sun will change Earth's climate, okay? And it might make it, uninhabitable here. Nearly all of Earth's energy comes from the sun. So energy that's in the oil and the gasolines and the coals began because of the sun. Are there, wood even in plants is stored up sunlight. So yeah, the fuels that we use. And the sun's atmosphere is very thin, and it even extends past the Earth's position and extends out quite a ways. And so things like magnetic storms, the solar winds, these sorts of things can have effects here on Earth. It can interfere with our radar and our satellites and things like that. So yeah, it's very worth studying the sun. Okay, so distance and size, some basic kind of physical properties of the sun. To learn kind of to get the true distance, we need to get that apparent shift in its position. That's termed parallax, if you remember, right? That shift is parallax. So say if we were kind of looking and we were interested in a particular star, we would take a photo of it as Earth is in a position in its orbit around the sun. We'll take a picture of that star, and then say 6 months later, when the Earth has revolved, you know, another 6 months in its orbit, take a picture again. So you're getting a picture of the same object from a different viewpoint, okay? And again, remember, it makes it look like the object is shifting, that apparent shift that's really due because the observer changed positions. That was known as parallax, okay? So we can use parallax and some other distance formulas, even Newton's gravity formula. We can get at the masses. So there are some ways that we can figure out some physical properties about the sun. One thing they talk about here is the transit of Venus, where Venus was seen as trekking right across the disk of the sun, and you can get, you know, a position marker when you do get these transits. But yeah, so being able to measure the planet's parallax shift using Kepler's third law, right? You can find the distance, so that relationship of the orbital period squared equal to the semi-major axis, which is distance cubed. Remember Kepler's third law. And from that, you can get distance, right? You can get that with that. So Kepler's third law becomes helpful in getting the distance. And so all of these physical kind of properties together, we can determine the density of the sun. Okay, so this is mentioning the transits of Venus, so you can track it and be able to get the sun's kind of diameter worked out nicely in some familiar kind of units. But getting at the density. So you'll need the mass of the sun and you need its diameter in order to calculate density. So I want to run this through for you. Not that you're going to be calculating any of this, but density is mass per unit volume. That's a physical property of matter. And I've got here a list of some calculations on how we can arrive at that. So in science, you're given some information, okay, and you're going to be given a lot of information about the stars and the planets and that, and you got to think to yourself, well, how do we know this? I mean, no one's ever gone and visited the sun, or they can't set foot on the sun, sort of thing. So how do we even know any of this? So we use to calculate density. Back up a little bit further here. Some things we need. Okay. To get at the density, which is mass per unit volume, okay, you need, of course, the mass. That's the top number. And in order to get the volume part, we end up needing the diameter. Okay, so let's see how we're going to go about that. We need the mass and the diameter, because from the diameter, we can get volume. Okay, and density is mass per unit volume. So the first thing we do is we take a look at this small angle formula to find the diameter. Now, this calculation, a lot of these equations are in the back of your book. You've got a little math reference cards in the back of there. So that's where I'm pulling this information from. So you should have these. But to start us off, there is an equation called the small angle formula where we can get at the diameter. So we would take, in this equation, we've got the angular diameter, the parallax, which can be observed. You can observe the parallax, that shift. This is a constant here, 2.06 times 10 to the fifth. Linear diameter, okay? We're trying to get at the linear diameter. And divided by distance here. Now you can get distance by Kepler's third law, as I mentioned, by observing the orbital period of your planet, okay? And that number gets squared. And that's equivalent to the semi-major axis, which is lowercase a, cubed. And so that is distance. The semi-major axis would be the distance of the planet from the sun, semi-major axis. So this could get us some distance in there, okay? And then we'll get at the diameter by rearranging all of that. So once we've got our diameter, know that the volume formula looks like this, 4/3 pi r cubed. Now r stands for radius, and radius is half of the diameter. So we got our diameter, we can get our radius and plug that formula in. So we have the volume portion of our density equation here, the volume. We've got that part done. Now it's the mass, and this is where Newton's gravitational force law comes in. If you remember that one, I wrote it up on the board, where the force equals the gravitational constant, mass 1, mass 2, so we're getting at the masses there, divided by the distance squared. So we had our distance from up here, okay, it can get plugged in. The g is a constant, and so you can get at what that force would have to be to keep the planets in their orbit with the sun, so you can figure out the force, that would be given, and then you can determine your mass. And so then now you have what you need to go ahead and calculate the density of the sun. So it's a multi-step process, but mathematics that we can easily use to calculate the density of the sun. You do need the mass, and you do need the diameter. And from that roundabout way there, you can calculate the density of the sun. So mass and diameter will do it for you, okay? You're not gonna have to calculate that, any of that. But I did want to take the moment to show you how it's done, how all of this is done. So there is a process behind it. It's just like, how will we even know the density of that? So they do mathematics, physics, all of that does go into astronomy and our understanding. So, okay, so that is one way that we can take a look at that. And so the origin of sunlight, sun's surface does glow for the same reason that makes the coils in your toaster glow hot. Okay, so the coloration that we see, different colors will depend on temperatures, as we're going to see when we do study the stars, that the colors, there's actually a category where they put them kind of classified by colors, which will tell us something about their temperatures. So different parts of the sun's surface glow slightly different colors, and that's depending on their temperatures. And we'll have more to say about these temperatures. Okay. First, we're going to take a look at the atoms and the kind of subatomic particles and see what's going on inside of these gaseous kind of atoms. But the atom has a very kind of compact nucleus at the center, and the nucleus contains protons and neutrons. So it might feel like a little chemistry lesson here for you, but the protons are the positively charged particles, the neutrons are neutral. They don't carry a charge. So that's what's in the nucleus of our atom. And then here we have the very low mass buzzing around electrons in definite discrete shells, energy levels, or shells we call them, kind of buzzing around outside of the nucleus. And these electrons can, when they get excited, jump up to higher energy levels, okay, and emit energy. and then they can fall back down to its stable ground state. It can't stay excited forever, so it eventually will fall down to its ground state, very stable state, and then that energy gets emitted. So the electric fields that kind of surround the protons and the electrons that they're producing. So static kind of electro, if they're saying run a comb through your hair, and you're getting this electromagnetic radiation, kind of the sparks and that kind of thing in there. So kind of that sun, okay, is very, very hot. And we'll be kind of using our temperatures in Kelvin for these things. But the protons can make electromagnetic radiation, but the electrons are so tiny, so lightweight kind of thing, that they're the ones that are buzzing around and doing any kind of communication and creating that kind of electromagnetic radiation. They're the ones that are the active participants in the atom. So a little bit about the atom there, but that ground state is sort of its stable state. So here we go. We got particles that get these atoms linked together that can form molecules. So you get some chemical bonding occurring, and it can be sort of an ionic type of a bond where you're transferring the electrons from one atom to another, and that kind of keeps them bonded together, electromagnetic force there, or they could actually be sharing, that's a molecular type of a bond in there, but we are kind of getting some thermal energy when this occurs. But a hot object is going to be more agitated. Those atoms are going to be buzzing around and moving a lot faster, okay, when it's hotter. Okay, so the heat you feel is thermal energy, and it flows. So heat is like energy in transit. It is flowing, and it's always flowing from areas where it's very hot or high temperature to areas of where it's cool, colder temperatures, lower temperatures. Okay, so in transit, think of heat as energy in transit. It's flowing. Temperature is actually related to that motion of the electrons, so that average speed of the particles in there. So the particle motion, kinetic energy, the speed, that's temperature, versus heat, sort of the transfer of that energy. So we end up using, astronomers, as you'll see, use the Kelvin scale, Kelvin temperature scale, where absolute zero is written as 0K, okay, and if we were looking at that in Fahrenheit, that would have been minus 459.7 Fahrenheit. That's pretty darn cold there. So yeah, but the Kelvin scale you might not be real familiar with, or you might be, but water freezes at 273 Kelvin and water boils at 373 Kelvin. So what we do is, why they use the Kelvin scale is because it relates to that kinetic energy, the motion, the particle motion. And so that's directly related to the motion of the particles of our atoms. So that's why astronomers like to use the Kelvin scale. So in our little calculations, you'll see Kelvin pop up frequently. So temperature, heat, and what we call this black body radiation. So a black body is sort of an opaque object. So opaque means that light's not going through it. An opaque object that is a perfect emitter in all wavelengths of radiation and a perfect absorber. Okay, so perfectly opaque emitter and absorber of radiation. Perfect emitter, perfect absorber of radiation. That's called black body. It doesn't have anything to do with the color of the object, but that is known as black body radiation. It actually refers to glowing objects, how much they're emitting, how much they're absorbing of this radiation. So there are a couple laws in here that describe how black body radiation works. So we're relating energy, temperature, and then the wavelengths of the electromagnetic radiation. So two laws in here. Now wavelength of maximum intensity, okay, so we got to think about the wavelengths in there. What its maximum intensity is, okay, where it radiates the most energy, that'll get used in the equations. But Wien's law is one of them, Stefan Boltzmann's law is the other. Wien's law is relating the temperature of an object to the wavelength. And so this one is saying the hotter the object, the shorter the wavelength, okay? We kind of looked at some of this when we looked at the electromagnetic spectrum. Those that had a lot of energy had very short wavelengths. So think of the gamma rays, the X-rays, ultraviolet rays, very short wavelengths. Those are high energy. They're also going to be high temperature as well. So Wien's law is looking at the temperature and the wavelength, okay? And I'll kind of draw those out for you here in a second. But so hot stars look bluer than cool stars, okay? Because of the wavelength, right? So a hot star has a shorter wavelength, which on the visible spectrum would be towards the blue and violet end, right? Versus a cooler star or cooler object, more towards the red or the longer wavelengths. So it would look kind of an orangey reddish color. So hot stars look bluer than cool stars. So here we're putting the colors with the temperatures now. That is a direct relationship to the wavelength in there. So yeah, so next one, Stefan Boltzmann law. This one's relating temperature to energy. Again, so another relationship. Hotter objects emit more energy than cooler objects. So it's a combination of kind of those two. I can pop that under there. Radiation laws, black body radiation laws. Try not to zoom out too much. I want you to be able to see everything from the board there. Hopefully that's showing up. So Wien's law, that first one up there, and again, these are in the back of your book, but that little lambda, so that little backwards looking y, upside down y, is lambda, and then max. So wavelength of maximum intensity is what that stands for. Here we got a constant, 2.90 times 10 to the 6 nanometers per second. So nanometers, very small. That's a good unit for, you know, a wavelength in there. Divided by the temperature, and of course the temperature is going to be in Kelvin. So here you have where it would be the wavelength of maximum intensity being inversely dependent on the temperature. So the higher your temperature, the shorter your wavelength, right? That's an inverse relationship, inversely, okay, to the object's temperature. Okay, that is Wien's law. Okay, Stefan Boltzmann's law is taking energy and relating it to temperature, and it's a directly proportional thing. Okay, so we have a little symbol here, a little sigma symbol, and it's a constant, 5.67 times 10 to the minus 8 joules per second meter squared, Kelvin to the 4th power. Okay, that's a unit for this constant in here. So energy, E, is proportional to the 4th power of temperature. So that constant times the temperature to the 4th power, of course temperature's in Kelvin, right? Everything's going to cancel, to where you are going to get your energy, okay? Joules, kind of, joules will be the energy output. So it's proportional, okay? So hotter your temperature of your object, the greater the energy that's going to be released. That's a proportional relationship. And the wavelength was an inverse relationship, wavelength to temperature. So Wien's law and Stefan Boltzmann's laws. Okay, so kind of in summary for that. So the hotter the object, the more energy it releases, and the shorter is its wavelength. That's a culmination of both of those laws together, okay? And that has to do with temperature, wavelength, and energy, okay? These are some black body radiation types of laws. And here's some nice little figures showing you that maximum wavelength of intensity in there. More blue light than red kind of is going to give your star a blue color. So now look at our temperature. Okay, our temperature is at 7,000 Kelvin. You might not be able to see that, but you do have the PowerPoints for this on Blackboard. But at a temperature of 7,000 Kelvin, that's pretty hot. So that's going to have a wavelength of maximum intensity more towards those shorter wavelengths, the blues. So it will look bluer, okay, than a cooler star. Here we have a star at 6,000 Kelvin, so a little intermediate. Its wavelength of maximum intensity, okay, we're kind of in the greenish hue for this one. So that makes a big difference there. And then this one, even cooler. I mean, 5,000 Kelvin is still pretty hot. I mean, we're talking about stars here, but cooler in comparison. So 5,000 Kelvin. Notice where its wavelength of maximum intensity is now. So this is a cooler star. And so you're going to have the maximum intensity at a longer wavelength. Remember, that's sort of an inversely relationship. So you're going to see more red wavelength, that's where it's maximum, and your star would look kind of red. So we can actually relate temperatures of the stars to the colors of the stars. Okay, so that's what they're talking about here. Orionis, Alpha Orionis, so using that proper kind of way of naming of the stars, if you remember that. And it's also known as Betelgeuse, versus Beta Orionis, also known as Rigel. So kind of looking at that, Rigel produces more energy, so it's going to look more blue. Betelgeuse is going to be sort of the reddish color. Okay, so it's a cooler star. Okay, so that's something that we will classify stars, and we'll use sort of a color way to relate to their temperatures. So, all right. So looking at then wavelength of maximum intensity, and kind of relating that to the sun. So let's look then at the sun's surface here. It looks kind of mostly smooth, but the closer we get up to it, it actually is very granulated look to it. But the sun's gaseous from its outer atmosphere right down to its center. So it's in just this huge, giant ball of gas, okay? Mixtures kind of gases, and we'll look at the compositions in a bit. But the photosphere is sort of that portion of the sun that light's actually coming through, the apparent kind of surface of the sun, the photosphere. Here, where light's able to make its way through. There are other parts of the sun that are so very dense, of course, because it's under so much pressure, that the light can't escape from it. But the photosphere, it's able to emit plenty of light, okay? It's about less than 500 kilometers deep, or 300 miles deep, okay? These sunspots that I mentioned, that Galileo actually did track some of these sunspots, but they are regions of the photosphere that appear a little bit darker than the rest of the sun. So we're taking those to be slightly cooler areas. I mean, we're still talking about the sun, so it's really hot, but slightly cooler in comparison to other regions on the photosphere. So those are some sunspots that we're going to look at some solar activities with that. So this granulation, though, visual kind of pattern to it. It looks kind of like there's a lot of convection happening, and so that's what they're actually finding out, that it is a convective sort of region with the motion of the energy in that energy flow, sort of driven by this energy flow in the sun's photosphere. But what it is, and they'll probably talk about it, and they might have a nicer picture here. Yeah, right here. So the granular kind of bright spots are where there's rising hot currents of gas. And so think of a boiling pot of water, how that water begins as it heats up to rise, right? Hot rising gas will rise up in a current, and then it'll get a little bit cooler and it'll sink back down. So cooler gas is going to sink back down. So we're setting up sort of this convection cell where the hotter rising gas, okay, it's going to rise up, forming the brighter kind of granular surface, and then it cools, and that's going to be these dark kind of in-between regions in here, giving it sort of the sinking edges there, a granular kind of a look to it. But this tells us something about the circulation of the energy in there. It's a convective region, at least in this outer kind of photosphere portion of the sun. So rising hot currents and sinking cooler currents of the gas, creating a granular sort of a surface on there. So convection, a process of convection. Yeah, right there. That word convection. Hot, rising currents of gas, and then sinking cooler, creating that cycle, that convection kind of cycle in there. That is evidence that energy is flowing upward with these convection cells, and then from below the photosphere of the sun in there. So it tells us something about the circulation, at least in the photosphere. Okay, so light, matter, and motion. And so on this one, we're kind of taking a look at light and the study of light. We really kind of talked about that, how we used our telescopes and our spectra to really tap into all of the light. But these electrons and other charged particles produce light when they either change speed or they change direction, because those electrons are buzzing all around. So we can get some variations with these electron shells that I mentioned before. So the Coulomb force, this is an attractive force between the atoms. Remember that the protons kind of had, if you lose an electron, which is a negatively charged particle, your little ion becomes positive. So a positive ion is missing its electron, okay? And if it gains an electron, it becomes negative. So it can create these little ions that we talk about. So in order to bump an electron off, right, it takes some energy to do that, to really knock your electron out of its shell out there, away from its nucleus. So to ionize it, you need a distinct amount of energy, okay, because it's staying, it's moving around, but it's staying around its nucleus. It's attracted to its nucleus from that Coulomb force, okay? It's attracted to it. It's kind of its binding energy in there. But it can get ionized and knock that electron completely away from its nucleus. So how much energy is needed to do that is what it's looking at there. So just depending on how far away from its nucleus it is will depend on how much energy you're going to require to knock it to the next energy level. But I did mention that that lowest energy level is called its ground state. That's where it's nice and stable. But it can get energized though. But each little shell only permits a certain amount of energy. This is kind of the quantum mechanics that they talk about. A certain amount, and I mean it has to be exact or it just passes on by. the electron can't use it, okay? So only permitted orbits, okay, can occur here. Almost like a little stair step kind of thing that they talk about, but there's no in between. It has to be the exact amount of energy in order to bump it to another electron shell. And of course that's going to depend on what is in your nucleus, how many protons you have in your nucleus. So yeah, so they're looking here at the hydrogen atom. It has one positive charge, and the electrons kind of, you know, not very tightly bound on that one. A larger one here has 5 protons in its nucleus, so it'd be a little more tightly bound to the nucleus. So we're talking about discrete kind of energy levels are on there. So referred to energy levels, that's what it's saying there. You know, permitted energy levels. Okay, so if you're going to move your electron from a low energy level to a higher energy level, we're going to excite that atom. Okay, that's going to be excited. You've added energy to get that electron bumped up to the next energy level, or depending on a discrete amount of energy. Okay. And like I said, it can't stay excited forever, and so it will fall back down to the ground state, the stable state, and it's going to end up releasing that energy. Okay. So they can become excited by slamming into other atoms, right? So that would definitely slow their speed, change their direction. And so that does happen in a very hot gas when you got the high temperatures, you got the speed of those electrons really moving in there. So they can collide often and absorb a little packet of energy and bump it up to a higher electron shell, and then release that energy when it falls back down to its ground state once again. So depending on, you know, it does have to be the exact amount. So, you know, here's a permitted orbital, 1 shell, shell 2, shell 3, shell 4, but it has to be an exact little photon, a little packet of energy that is just right in order to bump it up, right? There's no in between. It has to be the right amount of energy, okay? So this one, and they're doing a nice thing here with the drawing. See how that's a longer wave? So bumping it up to the first energy level, not requiring all that much energy, so you're seeing that the wavelength is longer. And this next energy level, the wavelength's getting a little shorter. It takes a little more energy. And then to bump it this far away from its protons, I mean, the protons are trying to keep it on there. See how short that is? That means it's a greater amount of energy to bump it up to the next outer energy shell for our electron. So yeah, it has to be exact though for its permitted orbital levels there. Just right. Yeah, so like, I don't know, they got no thanks, wrong energy, and it just passes it right on by. And then there's one that's like, oh yeah, that's the right one, and it bumped it to its next shell there. And then can't stay excited forever, and it'll go back down to its ground state, its lowest energy level, and release that energy on its way. Okay, so ground state there. So sometimes those from one orbit to another, that's called a quantum leap in there. So a little subatomic particle motion and energy within an atom that can help us understand, really can help us understand what's going on with the wavelengths in our spectra. Okay, and they do have the Doppler effect. So the Doppler effect is a nice way. It's going to show an apparent shift in the wavelength in the spectra. So again, revolutionized astronomy by looking at the spectra. These little small shifts in the wavelength of electromagnetic radiation. You've probably heard of the Doppler effect. Certainly we've experienced it with sound waves, okay, but it happens with light waves as well. But say, for example, when, I don't know, a fire truck or something is blaring its siren and that's coming towards you, that pitch gets a little bit higher as it does, so it's changing its wavelength. As it's coming towards you, the wavelength is kind of shortening. The sound wave is shortening. As the fire truck passes you by, that pitch kind of lowers because there's a stretching of the sound waves. And this is the same premise for light energy, the light wavelength. So Doppler effect can detect wavelength changes of an object coming toward the radar or away from the radar. And so this can tell us something about the motion of our stars or our celestial objects and their speed. Just how fast are they traveling? So Doppler effect is fantastic help for us. Yeah, and they're mentioning the pitch changes. That's the fire truck. Little example with sound waves, but with electromagnetic light waves, they're what we call a blue shift or a red shift. So what's happening is as the object is coming toward, okay, either the person, or the radar detecting it, the wavelengths get shorter, and so that's what they're calling this blue shift. Okay, they're coming toward the source there, and if you're going away from it, okay, red shifted to longer wavelengths. Okay, so kind of like get the red out, you're going away. It's kind of how I remember that. But blue shift and red shift. I do have an equation for that. Again, you're not calculating any of this, but it is a formula that is given in the back of your book that will kind of explain what's happening with the Doppler effect and how we can calculate the speed of our objects that are either coming toward or away. So say maybe you have a car. This is actually what police officers use to clock your speed. They have those little hairdryer looking things that they point at your car, and they're detecting this Doppler effect, this radial velocity, we call that. The radial velocity. So where VR is the radial velocity in this equation, get that there, VR is the radial velocity, okay? C is the speed of light, okay, so I've written that out there. And then this delta lambda, so that's the change in wavelength. So just how much did the wavelength change? And compared to the laboratory condition where there's no motion for the wavelength. So that's the lab wavelength, it's not moving. So when you get a change then in your wavelength, that's going to help you to calculate the radial velocity. So the change in wavelength over the lab conditions with no motion times the speed of light, which is the same for all manner of electromagnetic radiation. Remember that. And so you can get, if that change in wavelength is minus or if it's positive. Again, you're not going to calculate any of these, but we talk about it being blue shifted or red shifted. So Doppler effect can tell us something about the radial velocity, the speed of our object, either toward, and it would be blue shifted to shorter wavelengths, or away, which would be red shifted to longer wavelengths. Okay, so from that, and it's only toward or away, it is not transverse to the right or to the left. That's transverse. It is not. It's only toward or away from the radar. Okay, so red shift or blue shift. Doppler radar can tell us that, so it can tell us the motion toward or away, and it can tell us the speed, the radial velocity of our object. Okay, so that's Doppler effect, very important. But what we can do is we can look at the spectra. That's what the amazing thing is. So reveals the motion of the wave, red or blue, right? But I want to get at, there's radial velocity, the spectra on this. Okay, so yeah, they can see that if it has shifted from its normal position to a shorter wavelength or a longer wavelength, then you can tell if it's blue shifted or red shifted respectively there, and you can get motion from that. Here we have a spectrum showing what type of element we have, what kind of atom, so the composition in our gas here. So the composition of gases in the solar photosphere and the atmosphere, and the motion of those. So here we are, we've got it coming through, and we're taking a look here, and we're seeing several little blips down here, and another little blip down. So you're seeing a little dark line, kind of these absorption lines in the spectra. So that means there was some sort of interference that absorbed those particular wavelengths in there, okay? So they could study it, and normally they don't really look at the colored version, they look at these little squiggly lines. That's what astronomers actually do study on this. But the formation of the spectra, there's 3 types that we talk about here. I probably will put those up on the board, at least with a little picture or something for you. But so 3 types. One's called a continuous spectrum, okay, where say we had an incandescent light bulb and we were pointing our little, oh, I don't know where I put mine, but my spectroscope had it, I thought. Here it is. Yeah. If you were to point that at an incandescent light bulb and make sure you got the light in the slit there, you would see a continuous spectrum. It was something that I tried to show you last time on my camera, if you remember that. But that would be a continuous spectrum, okay? But now let's say we had a bunch of little gas atoms around that light bulb, okay? Those kind of excited gas atoms are going to be absorbing some of our little wavelengths of this light bulb that's trying to get to our spectroscope. So those gases are absorbing certain wavelengths, and those are going to show up as little dark bands, these absorption lines, we call them, because of that interference of the excited gas in there. This one here would kind of be, actually, those excited gases are going to emit. They're very excited electrons, and they're going to emit some energy of themselves, and it's going to end up as these bright line emission spectra in there. So those are your 3 types of spectra. I'm just going to draw a little light bulb kind of in there. Maybe. Let's see if I can get this. So our 3 spectra, one is a continuous spectrum. 2, an emission. And 3, an absorption. Do my try to draw here for you. A little light bulb. Oh, I don't know, it's got some filaments in it, right? And it's putting out some light. So if we were to look directly at that incandescent light bulb, that would be a continuous spectrum, okay? The emission spectrum, so say now we've got this cloud of gas kind of, well, I'm going to put it over here. Put the cloud of gas off over here, so it's not interfering with our number 1. Okay, this is a cloud of gas. Okay. And number 2 is sort of an excited kind of cloud of gas here. So for number 2, kind of going through that excited cloud of gas, okay? That would be an emission spectrum. Okay? Absorption spectrum would be one that's going through, okay, to our incandescent bulb, okay? It's passing through the gas, so the gas kind of absorbing the light from our light bulb. And so that's going to give you the absorption lines in your spectra. So continuous spectrum, absorption spectrum, or you could get an emission spectrum. Those are your three basic types of spectra, okay? So maybe be familiar with the little diagram and how you would label those, okay? And this is just taking you through it again. So the dark absorption lines, when the sun or the Earth's atmosphere is between you and the sun's photosphere would be an example of that. So there's little interactions that happen that leave some little gaps, those dark lines of absorption. Photosphere itself, continuous spectrum, so an incandescent bulb. Or if you were to point that, I don't encourage you to point anything up at the sun, but even if maybe just put it out the window, sunlight coming from the sun out the window would give you a continuous spectrum. Okay, just some of the variety, those three variety of black body spectra kind of thing. Yeah, so this one's taking a closer look at the hydrogen atom. And you might not be able to see that very well, but it's got a series of very distinct wavelengths. And they've put them into some series. The Paxton series, the Balmer series, and the Lyman series. And they're in various parts of the electromagnetic spectrum. The Paxton series is more in the infrared region. Okay, so we can't really visualize those, but the spectra would show those. The Balmer series is in the visible light and going a little bit to the UV. We can see three lines of the Balmer lines. There's like a red one and a blue one and a violet one. So we can see those. So together, red, blue, and violet kind of make this pink color. So it actually, that object looks pink to us because of all that hydrogen in there. But, and then the Lyman series is in the UV electromagnetic spectrum region in there. But there are three lines in the Balmer series that we can actually see because they are in the visible light region. Okay, so this is nice. Here's the Lyman series, so definite exact wavelengths for each one of those. The Balmer series, there's the purple, so the violet, the blue, and the red, so distinct wavelengths. And then all these in here are more towards the infrared, but distinct spectra of the hydrogen atom. So every single wavelength would be the same for any hydrogen atom that you would see. The spectrum would appear like this. To our eyes, we would really only see three of those lines because those are the three in the visible portion. But this is the spectra of hydrogen. So if an astronomer pointed, its telescope and its spectroscope towards an object and got these set of spectra at these particular wavelengths, they knew that the composition of that object had hydrogen in it. And there's a unique set of these spectra for every single element that we have. Okay, so we can determine the composition of stars because of their spectra. Okay, it really revolutionized the astronomical endeavors these spectra did. So yeah, but actually what they end up looking at, there'll be a little blip here, and that's an absorption line. A little blip here, another absorption line. So we do look at the spectra as graphs rather than, the colored and then the dark lines on there is how they look at them, though. So the chemical composition of the sun, trying to figure out and identify the elements that are in the sun by taking a look at those spectral lines. Okay, what wavelengths were they at? And so they were able to identify the elements in there. Okay, and one person who really helped us out with the temperature on the visibility of spectral lines was Cecilia Payne. She was later, her last name, she got married, Gaposchkin, I guess. But yeah, she was very influential in looking at spectra and figuring out that that related to a particular atom, element, okay? So we did be able to figure out the composition. So the most abundant elements in the sun, and hydrogen was the most abundant, on the order of about 91%, okay? Then followed by helium. So the sun and stars are mostly hydrogen, and then they do have some helium because they are converting their hydrogen to helium. And then some of them have carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and iron. Iron is like the end of the road for getting an iron core for a star we'll find on our star disk. So these are pretty much the elements that you would see in a star, a normal functioning star. But yes, this is very important in her that she did figure out, Cecilia Payne, so our first female astronomer that we've been talking about, and that she figured out the true composition of the universe, right? So the stars, mostly hydrogen, and then this little bit of helium and some other trace elements. But 90% are hydrogen, about 9% helium, and then we have some trace elements. So the most abundant ones are hydrogen and helium. But amazing that we could use the spectra and identify certain chemicals in it, in our objects. Okay. The chromosphere. So the photosphere lies above the photosphere. We've got that chromosphere. Okay. Defining the kind of the lower edge is lying just past that visible part of the sun, which is the photosphere, the visible part. And that outermost layer, the corona, okay, which we don't always get to see the corona unless we get that total solar eclipse kind of thing going on. And then we can see it. But very, very thin in comparison to the rest of it. Let's see, the Balmer lines, they're mentioning again kind of a pink color overall. But taking a look at kind of some of the different levels, and they're giving you some of the temperatures there. Some ways that we can observe the sun, right? Because you're not supposed to look at the sun like Galileo did, and he went blind towards the end of his life because of it. But a filtergram is a photo that we can use that would give us a better look of it, kind of give us some detail of the upper layers of the chromosphere. You're seeing some little filaments coming off of there as well. Very nice to see with some sort of help that we can see the corona in there. Chromosphere, so the little spicules and the little flares kind of coming off. We do have new information coming in. The Parker Solar Probe has gotten closer and closer. I think it was launched in 2018, and it's on a trek to be where it's going to be about 4 million miles away from the sun, which is actually very close to the sun, and giving us new pictures coming our way because it's getting very close to it. But then coronagraphs, so ways to kind of get at the corona, because we can't see the corona because of the photosphere. The light's all kind of drowning out the corona because of the photosphere. Here we have some nice pictures of the sunspots, okay, trekking across the sun. So this is sort of an activity, a solar cycle that we look at with the sunspot activity. Okay, so a magnetic carpet, this turbulence below the photosphere, making these little magnetic loops, flicking solar wind out outward. And these can actually blow past the Earth too. And depending on how strong they are, they can interfere with our satellites actually. So our TV satellites and different things. So let's take a look at the sunspots. If I can get to that a little closer there. Yeah, so Galileo did take a look at him, and he was noticing that over time, the number of sunspots would change. Their latitude positions on the sun would change over time. And the polarity of their leading poles of the sunspot would also kind of flip as time went by. So several things would happen, but sunspots are cool. We're still talking about the sun here, but they're cooler portions of the sun's surface in there. But so that word umbra, like a shadow, but it's just a cooler region. I mean, it's still very, very hot, but because of these strong magnetic fields that are going on. So a sunspot cycle is an 11-year cycle that, as you can see on this one, the number of sunspots will vary. So it'll go down to a very low kind of number, and then over time, okay, it will increase to a maximum and then begin decreasing again. And that's one cycle, and that cycle is approximately 11 years. It will vary. Maybe sometimes it's 10, sometimes it's 12 or 13, but on average it's about 11-year cycle. So you get your minimum to a maximum, back down to a minimum, and it starts over again. The cycle starts over, a minimum to a maximum, back down. And you'll see that. So this is like 1950 through, almost this kind of old PowerPoint, halfway between about 2005, I guess this one ended. So that's one thing. The number of sunspots will change in this 11-year cycle. This one down here, this little butterfly-looking figure, is where the latitude changes. So here we have a beginning of a cycle, and you kind of see them at 30 degrees north and south latitude of your sun. So here's 30 degrees north, here's 30 degrees south, and then they sort of migrate towards the equator, right? So they move closer inward to the equator. And then a new cycle begins, and they're starting farther and moving towards the equator over this 11-year cycle again. So we really do see the change in number and the change in location of your sunspots over time. Okay. And I don't know that they maybe showed it, but there is a polarity, kind of a flip that happens in the pair members of the sunspots within a hemisphere that will change. Let me get this little image in. Okay. So here we have that convection kind of welling and bubbling, the motion, right? The welling up, convection, rising hot currents of gas, and then the sinking back down. So we've got sort of that convection going on. The sun's photosphere is 5,800 Kelvin, and then that little sunspot, 4,500 Kelvin. So it's just a little bit cooler. I mean, that's still really hot. But look at the loop kind of that it makes there, a magnetic field, okay? This loop, kind of a magnetic dynamo going on. But these actually do have polarity, North Pole, South Pole, okay, with that magnetic loop that's happening. So it is kind of driven by the motion within the sun's rotation that's going on in there, kind of getting all wrapped up, and then squirts out these sort of magnetic flares, and you've got a reversal in the sunspots, North Pole, South Pole, kind of leading in a hemisphere. That's another thing that does happen with this cycle. Now here they're throwing in the Zeeman effect that gives astronomers a way to measure the strength of the magnetic field. So you see the splitting, okay, of the spectral line. So they know that there is a magnetic field that's causing a disturbance in the normal wavelength in there. So they know that there is some sort of a magnetic field happening in here. So that sunspot cycle appears to vary and affect the climate. So there was a time in there, we call it the Maunder minimum, where there were very, very few sunspots on the sun. And this extrapolated into our little ice age during this time. So it affected the climate. So the sun wasn't putting out as much energy during that time, and they're trying to correlate then fewer sunspots on the sun, less energy output affected our temperatures here on Earth. Okay, so Maunder minimum, few sunspots, and we got really cold winters. That was sort of the little ice age in there. And then there was a time, you know, winter temperatures, warmer winters. So this correlation, that number of sunspots can have something to do with affecting our temperatures and our climates here on the planet. And that was something they did see and correlated with the Maunder minimum in there. So here is a magnet with some iron filings. I actually did bring mine myself that you can look at. That it really does look like a magnetic field. So here I have some little iron filings, and I've got a magnet under here. And so if we kind of motion that around in there, it's going out one end and back in the other end, a North Pole and a South Pole on this. And that is kind of what those sunspots do look like. And so they're pretty confident, yes, that is driven by this sort of a magnetic dynamo of rotation, differential rotation within the sun. So I want to show that here. So this is the Babcock model, where here you have the equator, where the photosphere is rotating fastest at the equator, and then mid-latitude a little slower, and slowest of all at the poles. And so this is like twisting up and turning up the magnetic fields within the sun, they're saying. So I think they'll show that differential rotation, fastest at the equator, slowest at the poles. That gets it all tangled up, and it's kind of this dynamo effect that creates that magnetic field, and then it'll pop out and loop back in, creating those sunspots. And so this is sort of the sun's magnetic kind of cycle of that dynamo effect, the deep convective zone, clearly related to the magnetic field in there. And that's called the Babcock model. But noticing how in each hemisphere, the leading spot here is magnetic north, the leading spot is magnetic south. And so you get like a 11-year reversal of that. So if currently the northern one is the leading, okay, in the northern hemisphere, and the southern's the leading in the southern hemisphere, you will get a reversal of that, okay, after a cycle, after 11 years. It'll like flip-flop. Okay, so that is thought to be tied up into this sort of magnetic dynamo that they talk about. That's the Babcock model that they're talking about. So here we go. We got the rotation of the sun, which is differential. I mean, it's a completely gaseous object. So the equator region is traveling faster than the poles, and it's like getting all tangled up. Okay, many turns of a magnetic field, it's all tangled up, and then these pop out from the surface, creating the sunspots. And so it loops kind of out and comes back in, and so we're seeing that pair, that sunspot pair. And so this is really the Babcock model, employing differential rotation, right, of the solar surface, and the magnetic dynamo, that twisting up, for the formation of our sunspots. And it's a good model that seems to really explain this 11-year cycle. And so after 11 years, then it seems to kind of untangle, and then that cycle starts over again. Okay. They're just kind of showing these same things. So here we go. Each cycle, those sunspots are seen more 30 degrees north and 30 degrees south, and then over the time, they get closer and closer into the equator, and a new cycle starts again. So getting all wound up and then repeating that process in an 11-year cycle. So that's kind of a model for the sunspot cycle. Some other things, the beautiful aurora, powerful phenomenon. So solar magnetic fields, when they interact with the Earth's atmosphere and creating ionization of those ions, beautiful phenomenon that we do see, the northern and southern lights, we say. Some flares happening here. I mean, here's Earth in comparison, and then these flares are phenomenal. And some of the images that the Parker Solar Probe is already bringing back to us are absolutely gorgeous. Getting a really close-up view of the sun. Yeah, so some of these little ooh, and that one's in RUV imagery on that one. So the weather, solar wind, and different things coming from the sun. Tremendous amount of energy in those arches that they put out. Okay, let's see. So out of this chapter, a key take home for this is that we needed many laws, mathematical relationships, techniques to get a good understanding of our star, the closest star to the sun. So we ended up using some parallax to kind of help us with some physical properties of density, Wien's law, and Stefan Boltzmann's law to get a grip on temperature, wavelengths, energy, amount of energy coming out of there, of the sun, atomic structure, so what was happening with the electrons and how that was affecting the wavelengths, okay, the spectra. Kirchhoff's laws, so the black body spectra, so continuous emission and absorption, so we were looking at those as well. The Zeeman effect was the little splitting of a wavelength, which meant you had a magnetic field spiraling in. The electrons were being affected by a magnetic field. So we really had a lot of math that went into this, but you're really not calculating any of those in this one. I'll tell you when you'll have to calculate something, but not for these. These weren't anything you'd calculate. But I like to write the equations so that way you have it in a mathematical equation rather than just the words of the relationship. Having both of that together is actually very useful. So that was a nice look at our closest star, the sun, and you'll find that they use the sun as a reference for the other stars. So this is a nice place to begin, is closer to home with our stars. And then the next chapters, like I mentioned, we're going to be jumping to chapter 9 and then 10 and 11 to continue with our star unit. But we'll be branching out, taking a nice look at just how a star is born, okay, so what's going on internally, and then we'll take a look at the family of stars, so many characters in that, and then we'll take a look at the deaths of stars. So stars are born, they live out their lives in spectacular ways, and then they do die in various ways depending on their sizes, okay, so lots to get to in our star unit, but this will conclude chapter 5, and I'll see you next time. Thank you.